the basic theory of Partizan games. And so let's begin with a recap. So, what games are we talking about? These are two-player, turn-based, perfect information, finite, acyclic games. And also, they're partisan, so the players left and right have their own moves, regardless of who moves first, kind of like black and white in Go. And we're playing under normal play, so the player who can't move on their turn loses, or equivalently, the person who makes the last move wins. Those are the games and how we're playing them. Some terminology. An option is a position you can move to from a given position G. And as before, I might say game when I mean game position. This is pretty standard. And in using symbols, I'm going to use this sort of congruent symbol to mean like is exactly the same or is exactly the same game tree at least. And these curly G's represent sets of options. So curly G L is the set of all of the left options, all of the positions that left can move to, and similarly for right. But if we want to write individual games, we won't use that curly font, and we'll instead just write like G sub 1L as a left option, G sub 2L as another left option. We might write something like that. And this bar separates the left and right options. So we have games, they have outcomes under perfect play, and so it just tells us who has a winning strategy. And there's this little table here, because if we start with, say, right moving first, then we have, someone's going to win. Either right will win, so that's the first player, or left will win. And similarly, if we played the same game position with left moving first, maybe under perfect play, left will win, or maybe right will win. And so we have these four outcomes. N is for next player will win. L is left will win regardless. R is right will win regardless. And P is shorthand for previous player will win, as if this were like in the middle of some chain of moves. So here are some examples. 0 denotes the game with no options at all. And the outcome of that is P. There are no moves, so the next player to move will lose, so the previous player wins. -1 is a shorthand for this game where right can move to 0, but left doesn't have any moves. And in this case, this is a win for right, regardless of who moves first. Star, this is shorthand for, this is a symbol for a game where left and right can both move to 0, in which case the next player will win because they'll move to 0, and then the other player will lose. And one of the weirder games we investigated last time in a sort of whirlwind tour was Up. And Up is a game where left can move to 0, but right can move to star. And this is a win for left regardless of who goes first. If left goes first, she moves to 0 and the game ends because right can't make a move. If right goes first, he moves to star, and then it's left's turn, and left's move to 0 in star, and then again, right is faced without a move. So either way, left will win. Any questions about this notation or these outcomes before we move on to other complicated things? Okay. We can add games. So we think of adding two game positions as on each turn, or on your turn, you move in either game, and you just leave the other one alone on that turn. More formally, in this sort of sets of options notation, the left options of the sum are the union of all games of the form sub left option of G plus H and G plus sub left option of H. This represents left moving in G or left moving in H, respectively. And similarly for right, we take the union of the corresponding two sets. We can also take the negative of a game. So the negative of a game is the idea is to swap the players, like swap black and white. And what you have to do is you have to make sure you do that recursively when you're writing things in terms of the options. So the negative of a game doesn't only swap the sets, but it actually takes the negatives of all the games in those sets. That's why negative G is defined to be have left set, which is all the negatives of right options of G. Similarly for the right set.
Just to make sure I'm reading right, the sort of more squiggly font G is like a set of like the left.
Yes.
Okay, cool. Set of left side
Yeah, so
cards.
squiggly G, L is the set of all left options of G. And then when you do an operation on a set, we're doing it to all of the games in that set. So when we add H to G sub L, we get the set of all sums of the form left option of G plus H. And when we take minus G sub R, we get the set of all negatives of something in G sub R, G super R. Yeah, this notation's a little weird.
Is there a precise term for how that negative symbol distributes? Like in that like is how would you call that type of like distributive property almost looking thing?
I mean, so in talking to a stranger mathematician, I would just say that like these operations, like adding h or taking the negative, we just do it to all the elements of the set if we write it with a set of games. I would just say a sentence like that. If talking to someone who is familiar with functional programming, I would say it's kind of like we're uh, using map or on the operation to map over the whole set. Um, those are two ways I might explain it. Does that answer your question?
Yeah, it's almost like flood distribution, kind of like that's how I think of it. Like sort of
The other thing I
flooding,
could
kind of.
say is that like this minus curly gr, this is the forward image of the negative function on the set curly gr. So if you know about forward images and inverse images of functions from math, that's another way you could phrase it.
Okay, it's rather funny though. That would be a very long-winded way to say it, but yes.
Yeah. Um, and so we have negatives, we have sums, we may as well define difference in terms of both of those things. So when we write g minus h, that's just a shorthand for g plus the negative of h. Um, yeah. And so with this screen alone doesn't say that like negative uh, plays well with sum. Like in what sense is negative undo or differences undo sum? Well, we can learn more about that a little later after we review about comparison. So one definition we have for comparison, g is greater than or equal to h if for all games x, so this is like in any context of a sum, and for both starting players, either when left is starting or when right is starting, if left has a winning strategy in h plus x under those conditions, then she does in g plus x. Or way to summarize this is left can win g plus x whenever she can win h plus x. So this is like g is at least as good as h for left in any sum. That's what this definition is capturing. And it turns out we investigated, although I didn't write out a formal proof, that this is equivalent to a different definition based on the outcomes directly. So g is less than or equal to h if for all x, the outcome of g plus x is less than or equal to, I guess I swapped the order, but whatever. Outcome of g plus x is less than or equal to outcome of h plus x, where how do we order the outcomes? Well, we're ordering them by benefit to left. So that means that the right winning is worse than next or previous winning is worse than left winning, regardless of who goes first. That's the order of the outcomes that we're using. And these are almost the same. They're just phrased differently. If you think through, like that table of outcomes, you can prove this. It's just a different perspective. One thing about this order, unlike, say, real numbers or something, is that there are games that are incomparable. So incomparable means G isn't less than or equal to H, and H isn't less than or equal to G. One notation that's sometimes used is these like parallel lines. And sometimes in combinatorial game theory, we would say that G is confused with H. But you could also just say G and H are incomparable. Anyone who has done work with partial orders in math will be fine with that. And they might not be so familiar with confused with. But otherwise, we have our normal things. If G is greater than or equal to H and H is greater than or equal to G, then we write that G equals H. Now, I just want to emphasize, this does not mean that G and H are the exact same game position or the exact same game tree, but they're equal enough for the purposes of outcomes of sums. And G is less than H means G is less than or equal to H, but it's not equal to H, and similarly for greater than. So, to give you an example of what I said a minute ago, 0 is equal to, this is star plus star, but star plus star is not the same game tree as 0, because there are no moves in 0, and there are moves in star plus star, but they're equal in the sense that for outcomes of sums, they have exactly the same effect. And so this is, I encourage you to think about like fractions. Like the fraction 1 over 2 is equal to the fraction 3 over 6, even though they don't have the same numerator and denominator. And the game, you might say, game value of 0 and the game value of star plus star are equal, even though they don't have the same game tree. It's the same, it's an analogous situation. So this was very fast. Any questions about these orders or this notation? Okay. So last time we learned some interesting facts because this definition, as on the screen, this requires us to learn things about all games X and all those sums. And that's a whole lot. There's infinitely many games X to look at, so this isn't very practical. But we actually learned and kind of sort of proved some facts that actually we can test these inequalities by looking at the difference games and just checking their outcome of that one individual difference game. So G is greater than H when the outcome of G minus H is L. So G is better for left than H in all contexts when left will win G minus H no matter who goes first. And similarly for less than, G and H are equal when the second player or the previous player will win G minus H regardless of who goes first. And G and H are incomparable when the next player to move will win G minus H. And so, in comparison to sort of numbers, we might say G minus H is positive because it's greater than 0. We might say G minus H is negative. G minus H is equal to 0, but it's not identical. Like star plus star is not identical. It's not the same game tree as 0. And a combinatorial game theory term for incomparable to 0 is fuzzy. I don't know how useful that term is, and it doesn't really connect to any other analogies, but it's a weird term that people like. So I kept it in here. And so this is good because it reduces that question of how do we test things for all those games X into, okay, we just need the outcome of the single game, this difference. And this is very practical. So if you want to, if you want to learn, if you want to compare two games, you just look at the difference game. One thing we can do that I think I may have said in passing, but definitely wasn't on the screen before, is now that we know this, we can make a new definition. We can just say, so G is greater than or equal to H. If we read off those two rows of the above, that's L or P. Well, L is left wins no matter who goes first, and P is previous wins no matter who goes first, or rather, the second player wins no matter who goes first. And so what that means is that G greater than or equal to H exactly when left can win G minus H moving second. And I think this might be the definition given in Winning Ways. It is my least favorite of the three definitions we've seen because it emphasizes left and it emphasizes moving second as like a special case, and it doesn't feel like it's talking about all context and generality. It just so happens that by this theorem, this is equivalent to our previous definitions. Okay. So we have this ordering, and now we can start saying some new stuff. Any questions about any of the old stuff before we go into new stuff? Okay. So we just said, okay, we want to do a comparison. We just look at G minus H and see if we can figure out the outcome. But figuring out the outcome means we have to play that game perfectly. And so it's kind of a pain. Like if you want to know if G equals H, it would be nice if you had if you had something else you could do aside from, play G minus H perfectly. Like what if G minus H is really complicated? Then like playing perfectly might not be easy. And I want to sort of lean on that fraction analogy a little bit. If we had two fractions like 2/6 and 4/12, if you wanted to check if they're equal, would you subtract them and compare that with 0? That's not what you would do, or that's not what you'd usually do. You'd simplify them to lowest terms and then check, are their lowest terms the same thing? Like that's kind of why one of the reasons why we might simplify fractions to lowest terms. And so if we could do some sort of simplification operations to games in a way that preserves equality, then maybe we can't get to a perfect lowest terms, like single canonical form, but maybe we could at least get close. Maybe it's like almost unique, and like there's not too many options or not too much variation in like very simple ways of writing a game. And then it might be easier to check if they're equal by saying, okay, if they look almost the same in their simplified forms, then they're equal, or something like that. That would be a nice theorem to have. So to say this in another way, I'd say we have three objectives. First is, what actions would simplify a game while preserving equality? And then, after we do all that simplification that we can do, how many, and I mean this in a very broad and vague sense, most simplified forms can games have? So, this is not the theorem that we'll have, but you can imagine, let's say, like, maybe most simplified forms they'll almost be the same, except maybe some places will have 0 and some places will have star plus star, or something like that. If they're that close, then we could probably figure out equality pretty easily if the most simplified forms of games were pretty close. Something like that would be nice. But we don't know. We'll find out. And then the third thing, just to sort of add on, because if you have a fraction in lowest terms, it's certainly obvious, I don't know, say if it's like positive or negative, or something like that. So if we have some simple games that maybe we have in some very simplified form, can we find the outcome of, say, a sum of them easily? And summing fractions takes some work, and you got to remember how to do it. But we're summing games, and we'll see if we can do it efficiently, and how we can do that, and when we can do that, or something like that. Maybe not for all games. That's why I say like a sum of simple games, maybe like in easy cases. So that would be nice to have once we understand how we can simplify games. So those are the three objectives I would like to address. So the first thing in terms of simplifying games is about suboptimal moves. So so we have it on the screen, 0 is the game with no options, 1 means that left has an option of 0, -1 means that right has an option of 0, and that's it. So just an example, we could consider this game where, say, left can move to -1 or 0, and right can move to 1. And let's say we're taking the difference between that and 1, just to spice things up a bit. Then, what are the moves from this position? Well, left could move to -1 in the first component, or to 0 in the first component, leaving 0 minus 1, which is -1. Or right could move to 1 in the first component to get to 1 minus 1. Right could also move to 0 in that -1 component and leaving the complicated game, which I did not write on here, but just keep in mind that's another option. So these are just some of the options. And so from here, 1 minus 1 is 0, so that game is effectively over in the sense that it's a win for previous under perfect play, and actually there's only one line of play. But these other games aren't over, and right can make a move in each of them. And one of them, it goes to 0, and the other goes to -1, and either way, left doesn't have a move anymore. So these are some of the ways this game can go. But I want to notice, all the way on the left here, this -1, if this were in a different sum, maybe this -1 would help right win, even if left had some extra benefit. Like if we added, you don't have a lot of games at your fingertips, but if we added 1 to it, or if we added 1 to it, then this -1 would help right win because he would have a move in the -1 component. So if we're playing this game, this -1-0-1 game, in the context of some larger sum, why would left ever move to -1? I think I have some words to that effect. So yeah, the move to -1 in that component gives right a free move that he wouldn't have had if we just moved to 0 instead, if we're going to move in that component. So it's a bad move to make, no matter what the sum is, really. Why would you give right a free move? And so, say that -1 is worse for left than 0 in any sum, and that's what basically definition 1 for inequality is meant. So -1 is less than 0. And so this game, this -1-0-1 game, it should be equal to 0-1, because left should never make that -1 move. That shouldn't matter in any sum, because left would never make the bad move. So these should be equal, morally, or intuitively.
I just want to say I respect the comparison between morality and intuition.
Yeah, it would actually be horrendous if left made that move. I agree.
Yeah, just don't make moves that are left should not be making moves that are less than other moves that that she could make. That's kind of the idea.
It's the classic "don't blunder mate in one" situation.
We should outlaw losing in games, actually.
Yeah, yeah.
Okay.
That's morally reprehensible.
Okay, so let's outlaw it. Let's see. So there's a theorem, it's sometimes called the leading dominated options, which says exactly that. If G is this game where left has options like A, B, C, and right has some options, whatever, I, J, K, and this B option is greater than or equal to A, then G better be equal to G prime, where G prime, we just delete that A. Because if B is at least as good as A in all sums, then G and G prime without that A should be equal in all sums, because a perfectly playing left would never need to make the move A. She could always just move to B instead, because B is at least as good as A in all sums. That's the theorem that says formally what we were just talking about. And similarly for right, right should not make a move right doesn't need to make a move that's greater than or equal to some other move he could make, because he wants low moves. So we would say that option B dominates option A for left. It's at least as good in all situations for left. We can sketch a proof. So, how do we test that two games are equal? We play the difference game. So let's play G minus G prime. Let's say left starts. If left starts and left moves to A in the G component, well, B is greater than or equal to A. And so that means negative B is less than or equal to negative A. And so right can move to A minus B, which is going to be less than or equal to 0, and that's going to win for right. So right's going to win in that scenario. So I said that really fast because we haven't really talked about, like, we haven't had an example where negative is flipping the sign, but because it swaps the players and the inequality is based on the players, that should make some sense. Since B is greater than or equal to A minus B should be less than or equal to 0. So that's a good move for right to make. Let's say left starts and does some other move. She moves to like H minus G prime or G minus H. Well, in either of those cases, if left is making a move, that H is available in both G and G prime. So right could just move to H in the other component and get to H minus H, whatever that is, and that's 0. So that's a good move for right there. So if left moves first, right can win by following these strategies. Also, oh yeah, I see. This sentence actually was intended to also include the cases where if right moves first to any like IJK thing, then the second player, who would be left in that scenario, can also just mirror that move. And so in all of the cases, the second player can win. So the outcome of G minus G prime is P, and we know that that means that G equals G prime. So that was a kind of a quick little argument that encodes a lot of cases in a couple of lines.
So just to check that I'm integrating this knowledge correctly, this wouldn't actually help us with the case of 0 being equal to star plus star, right? That's still equal to 0, but we can't show it using this proof.
Correct. Yeah, star plus star does not have dominated options to delete. In fact, star plus stars, in star plus star, left can move to star and right can move to star, and so there's only one option on both sides. So of course there's no way for one option to dominate another because there's only one option for left and only one option for right.
So I guess this isn't a theory of everything for how to determine equality.
Right. No such luck. Speaking of star, let's look at star. So star, remember, is the game where left and right can move to 0, and that's incomparable to 0 because star is a first player win and 0 is a second player win. Well, because star is a first player win, and those are incomparable to 0, is what we proved last time. And we have this game up that I mentioned earlier. Up is where left can move to 0 and right can move to star, and I argued that was greater than 0. So we have those, and we were just talking about star plus star. Well, star plus star equals 0 by symmetry. The first player will move in one star, and the second player will move in the other star and win. Well, what about the game up plus star? So up plus star, we got to think through this. Left could move in the star component, leaving up, or she could move in the up component to 0, leaving star. So those are left's options. Right could move to star in the up component to get to star plus star, or right could move in star to leave up. And we just said above, star plus star equals 0. So I don't know, I may not have said this, but you can replace equal games in options and get equal games. So if you replace the star plus star with 0, you get an equal game. So up plus star is definitely equal to this game star up, bar 0 up. So that's a little bit of, that's sort of just writing out the definition of sum and replacing star plus star with 0 because it equals 0. But we can actually do a little more because we know that up is greater than 0. So for right, who wants lower values, 0 dominates up. So right would be foolish to move to up. Right should just move to 0 if he were ever going to move to up. So we can delete that dominated option and end up with just 0 there instead of 0 and up. So we're applying our theorem from the previous slide. So this is some nice simplification. It's a lot simpler looking than the definition of up plus star. Any questions about these steps before we do some next steps? Okay. So how would playing this game go? If left moves to up, then right's only move in up is to star. And since up is greater than 0, we can add star to both sides and say up plus star is greater than star. So what that means is that star is less than this original thing, this up plus star that we had. So star is better for right than the original up plus star. So this is a weird scenario. I'm going to say this again, slightly different words because it's important and confusing. So if left moves to up in up plus star, then right responds by moving to star, and star is actually better for right than the original game up plus star. And so if left is choosing to move to up, she must be ready for, like in some broader sum, she must be ready for right to move to star, even though star is better than up plus star for right. So left must be prepared for that good response. So in the big sum, if left is considering moving to up, she may as well be ready to move straight to whatever she'll respond to, however she'll respond to that good move, however she would move in the up that right could move to. Right wants to make his position better, so he may very well choose to move to star. And so left better be ready for that follow-up, otherwise why move to up in the first place? Why give right this better position than you started with if you're not ready to follow up? Well, the only move in star is 0. So right's response in star, left's response in star is 0. Because that's the only move you can make in star. And otherwise, left allowed right to get to star, which is better than up plus star, for no reason. So that would be foolish if left were not ready to go to this response 0. That is a lot of confusing words. Does someone want to rephrase the idea to make sure that you're following along? Can I get a volunteer? I know some of you don't have mics.
Admittedly, I lost you in the second half there. So, like, but I'll maybe try anyway. So, I followed you up to the computing equivalence with like star comma up for left and 0 for right. But what's the point after that?
So star is better for right than up plus star.
Yep.
And so if left is going to move to up in the original game, right will probably want to move to star because that's better than the original game was. And so, whoops. And so, why would. So, the question is really basically left would only move to up if she's prepared for this response. Like, right is responding to something that's even better for right than the original situation. And so, left better be prepared for that. And by prepared for that, I mean ready to move to whatever she can move to in that star that right's going to move to.
So
But
you
she can
use...
only move to 0
Yeah,
in
that's
that
true.
case.
In this case, this is a very simple case. But if
So-
she had lots of moves, then maybe she would move to her favorite move among them. Oh, also, I missed all of the chat earlier.
That's okay. It's not important,
Okay.
or at least not immediately relevant. It's,
Okay. We can come back to it later.
Sure.
So this is essentially why like a false anticipation of like a response from right in this case would like if you were to go with it, it would lead you to a suboptimal move.
Well, I wouldn't necessarily say suboptimal. Just, if you're going to allow right to move to something better than the current state, you better be ready for it. That's all I'm saying, really.
Okay.
And by be ready for it, that means like have some move available that's actually even better for you, right?
Well, maybe even better, it might be misleading, but like appropriate in the bigger sum.
Okay.
Yeah, maybe not better in all contexts, but like if you're playing this in some bigger sum and you have a lot of responses, you better, like among them, hopefully one of them is appropriate. And so this is kind of confusing, so I'm going to go to the sort of the notation, the formal thing I'm trying to lead to, and that might make more sense. So the idea, or what I'm proposing here, is that it seems like up plus star should be equal to, instead of star and up as the left options, we could replace up with where left is going to end up. Left is going to end up at 0 after right moves to star. So we replace it with 0 that it's going to end up as. And that should be the same for left in all sums. Because, like, as I said, if left ever wanted to move to up, she should be ready for right to move to star, in which case left is going to move to 0. So we may as well just say, like, okay, left moves to 0. Like, that's what happens.
Wait. So, okay.
Or if there were more options.
I think I got you now. Can I do a take two at summarizing?
Please.
Okay. So we know what right wants to do here, and that clarifies the set of dominated options for left. So because like, we can whittle down the set of dominated options for right, that also permits us to thereby whittle down the dominated options for left.
I mean, so this is not really connected to the dominated options discussion.
Is it not?
Like, not really. Like, because we're saying that star is better than the original game up plus star for right. But I'm not comparing two options after the fourth bullet point on the screen. I don't compare two options anymore. So the bulk of the slide is not really about dominated options because they're not comparing two options of the same game.
Okay, please hold. Thinking.
Sure.
And by please hold, I don't actually mean like you need to stop. You feel free to continue.
So I just got a one-word spoiler from the chat, and I'm going to take a pass at summarizing by saying it basically doesn't matter what order these events happen in. The like when you say you're bypassing the up-star exchange, does that mean that you could do it or not do it, and it like no, never mind.
Well, in the sense that I'm claiming that the game that has a left option of up and the game that has a left option like 2 steps down the road of 0, I'm claiming that those are equal. So in that sense, like, it doesn't matter if we're about to do up or about to do move 2 steps down the road. In the scenario where right improves his situation by moving to star in up.
So it is
not sure if
always
that's a
the
yes
best
or no,
option
depending
to
on what you're-
immediately respond to that up arrow by playing the 0 that's in star. The up arrow goes to star and the star goes to 0 by both players consecutively making their best moves always. And for that reason, the up arrow can just be simplified to a star. Or sorry, to a 0.
So it's a little more complicated, more subtle than that. Because in some big sum, maybe left's best move is
It's
not
not local.
to
right?
move to 0. Maybe left wants to move to the star that she always had instead.
Uh-huh.
Sometimes the star will be better in some sums. But when the star isn't better, or when left would consider
Sure.
moving to up,
Yep.
left better be ready for right to make a good response, and then left should respond in kind. Otherwise, what are you even doing moving to up?
Okay,
That's
so yeah,
all.
so it's not always necessarily the best idea to play locally, but when it is, you would still play that up goes to star goes to 0 exchange, and
Yeah,
therefore
yeah.
it can be simplified.
That's the idea. Yes.
Okay, I'm with you.
And so to write this thing we're talking about in more general notation, or in a sentence first. So if right has a response to a left move, that's at least as good for him as the original position was. So this is an important condition for this idea. Like, it's not just, oh, that's a nice response or the best response. That's a response that's so good it kind of obsoletes the original thing we're talking about. Like, if right has a response that good, we better be ready for it if we're going to consider this move at all. So left may as well assume that right would play that good response, even in the context of some broader sum, because it kind of obsoletes the original game when right makes that good response. And so the name of this theorem, as was hinted at in the chat, is bypassing reversible options. And I don't like the name reversible because we're not changing the order of time or anything. Like, we're not reversing things. It's just like it's reversing in the sense that right makes a move that's even better for right, or at least as good for right as the original position. So it kind of like obsoletes the original game in some sense. I don't know. I don't have a great defense of reversible. Axiomatic system is something.
An alternate way of saying it would be like right has restored all the value to him that left's move took away.
Yeah, I agree
So
with that.
that's kind of how reversible. That's kind of where that word
Sure.
fits in, but I agree that it is definitely confusing in some contexts.
Maybe more like adiabatic kind of would be more appropriate almost.
Adiabatic options. So to write this out formally, let's say G has left options like A, B, C, and right options like I, J, K. And for some right option of A, let's call it AR because it's the right option of A, G is greater than or equal to AR. So AR is less than or equal to G. AR is at least as good for right as the original G was. So that's like a good response to left moving to A. Well, if AR has a bunch of left options, the example we showed before just had one, but it could have many left options, like W, X, and Y, or etc., then we can replace the A with that like 2 moves down the line, all of those W, X, and Y, etc., and get this game G prime, and then G equals G prime. So if you were confused by all the words before, the too simple example, seeing this in front of you and digesting it for a minute might help. So let's take a minute to read through and think about it.
only the left options of AR copied over?
Right. Because it's like left is going to respond. Like, if left is going to move to A, they better be ready for right to move to AR, and AR is even better for right than the original G, so left may as well follow it up with W or X or Y or whatever. So, but yeah, so we only need the left options to copy over. Yeah, we're only talking about left moving first in this scenario. Now, I phrased this theorem in terms of like, you know, a left option A and right having a good response, but like there's like a mirror version of this theorem. But yeah, we're only copying one side options of AR in this instance.
And we're assuming that right would always play that good move because we're assuming that right wants to like sort of ratchet you into a game that's closer and closer to a win for right, of course.
Yeah, and in some broader sum. And so the subtlety that I'm not emphasizing here, but the subtlety here is that like maybe hypothetically right could have like a lot of great responses that are better than G for right or something like that. And we don't we just need to pick one of them. Like this is saying, okay, if there's at least one great response, we may as well assume that left would only consider moving 2 steps down the line. Like it doesn't matter which one we pick. Which like AR we pick. There could be many.
And if there were multiple, you could, in theory, consider doing this process for each of them in turn, right?
Well, you would get a lot of different games that G is equal to. Yeah. You get like G is equal to the G prime for one AR, and G is equal to a different G prime for the different AR. You would get a lot of different games, but you can't like do them in succession because there's no more A.
Well, no, but if A and B were both better, then B is still in the G you get after you bypass A.
I think. What do you mean by A and B are both better? I think you're confusing A with AR, maybe. Like if B has a good response BR, then yes, you could do it on B then also, if that's what you're saying.
Yes.
Okay, sure, yes. Certainly, if this theorem applies to like multiple options, like A and C or something, you could do it to A and then do it to C. Yes. Okay. Any other questions about this weird-looking theorem? And so just as a reminder, so one application of this theorem says that up plus star is actually as simple as star 0 bar 0. Like that was an application of this thing that I'm now claiming is a theorem in general. And as I said, there's a mirror version of this theorem for like some left option of G has a good left response that's at least as good for left, then right may as well skip past it, etc. Surprise, this is all you need to do. So, as Tusop was lamenting before, the deleting eliminated options does not settle questions like star plus star, we'd really like it to simplify to 0. But bypassing reversible options does. And so we have theorem, canonical form. If G, and this other condition is extremely important because a couple of like notes on combinatorial game theory, forget it, and then the theorem is not true anymore. You need to go recursively to all of G's options and the options of the options, the options, etc. If all of those have no dominated or reversible options in the sense of the previous two theorems, and the same thing is true for H, then if they're equal, they're identical. So this sort of gives you an algorithm for finding the canonical form of a game. Basically, like, go into the lowest level, make them, delete dominated options and bypass reversible options, and keep doing that until you've handled all the levels, and then you're done. Then it's in a unique canonical form. And just like fractions, then you can test equality by just looking after you're done with that.
You don't do AD minus BC and then look at it, examine equality to 0?
No, we don't have to. We don't have to look at the difference game. We don't have to look at AD minus BC, etc. And so I do want to emphasize, just in case you're interested in. So at the beginning of this talk, I reminded us of the types of games that we're looking at, and we kind of need like all of those conditions for this theorem to be true, as written. So, for instance, the simplest thing I would say is if we get rid of like finite, then this theorem doesn't work anymore, because if you can move to, like, let's say you could move to any natural number, then like each individual natural is dominated, but you can't delete them all because then you would delete all the options. And so there's no canonical thing, like which naturals do you delete? Your favorite bunch, but you got to keep infinitely many, so there's not a canonical form anymore, for instance. And if you delete like acyclic, then you need another simplification that we have not discussed. It doesn't apply in the acyclic case. But for games as we were talking about them, this is all you need to do. And yeah, it's very nice that there's easily findable canonical forms. Any questions about or comments about this before we move on? Okay, so yeah, like we said, you can just find the canonical forms of two games, or like try to keep things in canonical form as much as possible all the time, and then just check if those canonical forms are identical. And as I said, you got to drill down into the options and options and options. Here's an example. This game where left can move to, like, left moves to star and right moves to star, and right can move to the same thing. This game has no dominated reversible options, but its options do, and when you actually simplify it, it simplifies down to star. So that's like a counterexample to a more naive version of this canonical form theorem. Okay, great. And yeah, I'm not going to prove that this works. It's not. Yeah, the proof is not short enough that I could just like easily give it on a slide and have you all follow. But it's also not. It doesn't require any novel ideas. It's just sort of like, now that you know what the theorem is, if you lock yourself in a room and know how to write induction proofs, you could probably figure it out eventually. So, great. So that's two objectives down. We have ways to simplify games, and we have most simplified forms. It turns out there's a canonical form. So now that we have a canonical form, we can rephrase the third question slightly. Can we efficiently find the outcome of a sum of, not like all games, because like all games could be really hairy and complex or whatever, but like some pretty simple games that, let's say we already wrote them in canonical form, could we find the outcome pretty efficiently? That would be a good win for combinatorial game theory to have some theorem like this. So let's see what we can do. No. Sorry. What do I mean? I can make this precise. If we have very simple games where like x is a number, I kind of alluded to what some numbers like a half and 1 and -1 and 2, and like y is a number and z is a number, x is greater than or equal to y is greater than or equal to z. This is a pretty simple game if x, y, and z are numbers. And let's say we have a sum and difference, sum and difference of games like this, and you want to know, can left win playing first? It's p-space complete. This is it's too hard.
That's kind of crazy, actually. Like, that means that there's like a primality test in terms of like whether left can win a game playing first.
Yeah, this is
Pretty sure.
Could someone explain p-space completeness to me like I'm 10?
Sure. So just so if you have an algorithm that can run with a polynomial amount of space, a polynomial in the input, then so I was not prepared to do this on the fly, and maybe some of the others here.
This relates to P versus NP, and it's basically saying it's too hard to tell if left wins playing first or something.
Right. So in P versus NP, the question's about time complexity. So how long does it take? For example, like a simple example is like Sudokus. As the size of your Sudoku grid gets bigger, the difficulty of Sudoku is thought to get like harder and harder in a way that grows faster than polynomial. Whereas when we're talking about space, it's not the speed of the program, but it's rather the amount of memory that you need to know at any given time, right? So like I'm trying to think of a good example. Like, for example, the multiplication algorithm on paper doesn't require that much memory. Like, if you're trying to multiply two numbers together and you do just like, one digit multiplied by the whole top number and then the next digit multiplied by the whole top number and add all those together, it's quadratic in the amount of like space on the page that you need to write all those digits out and then do the sum. So that's an example of like
That makes perfect sense.
A polynomial space algorithm.
The
Got it.
p-space
P-space
completeness
complete.
part. Yeah, sorry, I'll let you do it unless you want me to.
No, please.
Oh, I was going to say the p-space complete part means that there exists some polynomial algorithm for any particular polynomial complexity problem that like basically turns it into this one. In other words, you can like if you have like some polynomial time problem that's completely unrelated, but it's in p-space and you know how to like solve this problem quickly, right? Then there's some polynomial time problem to convert the issue you're looking at into a problem of this form, which you can then solve quickly. But the
Oh
problem is
wow,
that
okay.
this is as hard as the hardest problems in p-space, at least, is
Right,
the issue.
right.
So we don't really have, as far as we know, a very fast one.
Yeah.
Oh, fascinating. Okay, cool.
So this is really hard. This is really bad. And so as a corollary,
Primordial indeed.
of this, which admittedly I think was proven other ways before, or at least independently of this theorem, Go endgames on an arbitrarily large board must be p-space hard, because you could build these simple positions as like a part of a Go board, and so they're also space hard. It looks like in the chat there's an explanation of p-space complete or p-space hard. Suppose you have an algorithm that can solve all instances of some problem up to some problem size S with an amount of memory M. And suppose that there's some finite number n, says that anytime the maximum size doubles, the required memory is multiplied by at most n, then your algorithm runs in p-space. Yeah, so that's kind of like Well, it sounds like it's bounding
That-
by a exponential, and
Yeah,
so
are we saying if it? No. It's bounding exponentially based on an exponential change in the input as well. We're saying each time you
Yeah,
multiply
so the
the
memory and time are
Oh,
growing
okay.
linearly
right.
as the exponential growth happens.
or polynomially, maybe.
Or polynomially, yeah, sorry. Not linearly necessarily, although that is a polynomial.
Yeah. Um, so this is sad, I guess. Like, okay, we have these canonical forms, and I didn't say it explicitly, but you may have guessed that games written this way, if X, Y, and Z are written as in canonical form for those numbers, games written this way are in canonical form already. But we can't we can't effectively figure out who wins a sum of things like this.
So the question that this yields for me is like, suppose I want to go and make a domineering solver. Like, is it plausible that I could canonicalize like a large table of common games and then just like store in memory um their what's it called, their outcomes?
Canonical forms.
Well,
Hey, their outcomes, yeah.
I'm thinking like could I make a table of the canonicalized forms of all of a whole bunch of games and plausibly store like that table in memory? I'm wondering like how many, like how easy how many things canonicalize down to one canonical form in practice. I don't know if you know the answer to that, but like I'm wondering if how big I could go in domineering before this table gets too big.
I mean,
Yeah.
you could do a lot. So, domineering is a bit. Domineering is special in the sense that, like, what do I say? Well, you don't have the definitions for me to make this precise, but like basically, there are large classes of game positions, including like the ones that are on this slide, that we at the very least conjecture domineering doesn't wade into. And so for domineering in particular, it's actually very amenable to what you're talking about.
Oh,
But like maybe domineering is much more amenable to it than like Go end games would be, or for instance,
I
or
see.
something like that.
Okay.
Domineering avoids. Domineering does not have arbitrary games that look like this, or at least it's conjectured not to.
Sorry, is there a reason for the selection of this XYZ form here? Like, you seem to be implying that domineering is easier than this. Is there something harder than this, or is this intended to encapsulate like the maximum possible difficulty of sums of simple games, or like
No. This is intended to be. This looks pretty simple. Like, like X is 5 and Y is 3 and Z is 2 or something.
right?
That's a pretty simple game to write down and to understand.
Hmm.
Uh and yet even when you restrict to games to summands this simple, you get piece-based completeness. Like
Yeah,
I
I
like I could give
follow.
you more games would be
Mhm.
yeah.
I think what I'm trying to ask though is like, is it fundamentally harder if you make the form harder?
Um so do you get like even harder results than piece-based completeness if I added more forms? Is that the question?
Yeah, I guess so. I don't know.
I
I don't.
don't
My question isn't exactly
I don't
completely
know.
formalized, but yeah.
Yeah,
Okay.
like
Okay.
I think there might be some other results of like if you take these other games, then you get like NP complete or piece-based complete or something. But like I don't know off the top of my head how you get worse than piece-based complete
Okay.
if there are results like that known.
Gotcha.
Yeah, I
But
guess you could. It could be the unicorn case of it being exactly the hardest problem in P space, which would be kind of funny. Like that would
well, I mean
like
that's what piece-based complete kind of means.
well, yeah, but like no, if it were no harder than that, it would be kind of funny.
No, that's what the complete as opposed to hard means.
Oh no, you're right. I'm sorry. I'm
Yeah, so
wasn't
with these
exactly. Yeah, I
particular
forgot
games
how
with
that
X,
worked.
Y, and Z, it is exactly like effectively the hardest problem in P-space. But like a priori, Go endgames could be even harder than that because they have other games in them. But I think like you could prove that Go endgames are piece-based separately, but I didn't get into that because that's not involving this fact.
Okay, thank you. That clarifies it.
But yeah, I guess the other thing I'll say to Swap is that like there are like measures of how hairy or complicated or whatever like a game is that like we haven't discussed at all, and like maybe like and some of those like Domineering does not reach.
Gotcha.
I guess the question to see, like, if you wanted to build like a higher complexity class out of these games, the question becomes like, how can you implement 3-sat with games? Basically, like that's how I would literally approach that.
Well, 3-sat is merely NP complete. Is that right?
Yeah, it's the canonical, according to Wikipedia, the canonical NP complete
Right.
problem. But just yeah, how would you like that if you wanted to build like the set of games which are like together are like NP space hard or NP space complete? Like, I feel like you would just pick a problem as hard as that or harder, and then try to implement it with I guess, a sequence of like games.
So
Not a sequence of games, or like a simultaneous system of games. It's very weird.
So P space contains NP. So like 3-sat is not hard enough. This is worse. Yeah. So
Okay.
yeah, like NP complete, like P space complete is no easier. Is like it may be harder because P space contains
Okay.
NP.
Yeah. I'm getting
So
my complexity
actually,
classes mixed up.
if you want to
Everywhere,
get
seems like.
if you want to get something worse than this result, like we have this crazy result that's like even worse, or at least seems worse than NP complete, just with like 3 numbers X, Y, and Z like this. If you want to get to like exponential time complete or something terrible like that, I don't know like if you can do that with combinatorial game theory or what the games would look like to get to there. I don't even know any exponential time complete like problem. I don't know that much about complexity theory. But yeah, I'm glad you brought that up so I could make clear P space complete is like worse than NP complete. Looks like something is going to appear in the chat. But I think so. Yeah, these are the same sources as last time. But I'm happy to, I don't know, take questions or other wonderings. Maybe I know the answer to some other question.
So back to the idea. This is kind of a basic question, but back to the idea of the in some broader sum. That's
Yes.
that's referring to like potentially some larger game or set of games that includes the one that you're looking at right there in front of you. That's
Yeah,
in
so
some broader sum is. Could you just go over that again?
sure. Yeah, when I say in some broader sum, which I'm trying to remember where I said that, but I probably said that multiple times. Like here, so the point is that like our uh like our definitions of inequality and our definitions of game being equal are about like G plus X versus H plus X for all games X. And so we're not just talking about like, when I say G equals G prime in this bypassing reversible options theorem, that doesn't mean like G and G prime have the same outcome. That would be boring and not saying very much. That's saying G plus X and G prime plus X have the same outcome for all games X. That's what it means. And so when I say in the context of a broader sum, I mean, we're not just looking at G, but we're looking at like G plus X. And so to connect this to the previous talk, we're not just looking at like one corner of a Go board, but like this corner of the Go board in the context of the entire Go board, where it's kind of being added to the rest of the Go board.
Right. Got it. Okay. Because every game is the sum of other games. And so there's always a broader sum that can be referenced, a broader game that you could look at.
Or at least for this, like for the meaning of this equal sign, it means the outcome of G plus X equals the outcome of G prime plus X for all games X. Not even
For
just
all
like
games X.
Go boards, but like any game you can imagine that fits the definition at the beginning of this talk.
Right. For all hack and bush, for all whatever. Yeah. Okay. Got it.
Because if we're just talking about like outcomes of G without adding an X, then kind of connected to what Tusop was saying before, like all we would care about is like less best move. Like in G, left has a best move. Maybe it has some equally good moves, but like there's a best move in G if we not care about sums of X. But if we have arbitrary sums, then like context could make some moves in G better in some contexts and different moves better in other contexts.
I'll go ahead and say the question that I asked above. I think I figured out the answer, but I said I wonder what closures under non-confusion look like, and by that I meant like if we take the closure of some game under all of the things that like are not confused with elements that are yet inducted into our closure set, like what would that look like? But I think the answer to that question is that's not even a well-defined thing in the first place, because if I remember correctly, last time you mentioned there's like such thing as a range of confusion, and like you don't have transitivity, so you don't even get like equivalence classes under non-confusion in the first place.
Okay, so that's something I can definitely comment on. Thank you for bringing it up. So first thing, like this less than or equal to thing is a partial order. It's definitely transitive. If A is less than or equal to B and B is less than or equal to C, A is less than or equal to C, period. That's absolutely true.
But confusion isn't, right?
Oh, yeah, confusion is not. Yeah.
Right. I'm talking about closures under, not under the equivalence operator, but rather closures under not being confused with something.
Yeah, okay. So one thing that's pretty close to what you're asking about, that I was thinking, and I didn't want to squeeze it into this talk, but I will mention because it is a good answer to your question. So one thing you could consider is, you might want to game. Let's forget about adding to other things or comparing to outside things. Let's say you just want a game that's comparable. That's what a way to say non-confused, comparable.
Yeah, comparable.
A game that's comparable. Let's say you want a game that's comparable to its options, and you want like all of its options comparable to their options. You want G comparable to its second options and third options and whatever, like all the way down. Like G is comparable to everything below it on the tree. That's a thing you could want.
Right.
And you could call that like like a hyper comparable game or something, where like all the G is comparable to all of its options and options of options, and all those are comparable, etc. So it turns out the hyper comparable games, I just made that word up, those are the games. Well, the technical term for those games in combinatorial game theory is numbers.
Okay.
And their canonical forms are like really simple, and in that game value discussion from last time where we had like 1.5, etc., the numbers are like the dyadic rationals, the rationals whose denominators are powers of 2.
Okay.
So, And all the hyper-comparable games, all the numbers are comparable to each other on like the number lines because rationals are comparable.
But
And so the numbers, the hyper-comparable games, are like a universe of games where they're all pairwise comparable.
and all of their options are
Uh,
as well. Is that correct?
yeah, and all of their options are as well.
Okay. But once you start trying to compare
So,
them to outside, to things that are not within that set, to games that are like to Star and stuff, you start getting
yeah,
uncomparables.
like
and
zero is not comparable to
okay,
star, and so then you have a problem. Even though like one is bigger than star and a half is bigger than star, but zero is not comparable to star.
right.
So star would mess that up. Um, but
Okay.
a good world of comparable games are the so-called numbers. Um, yeah,
I'm
and
wondering, is there like, can you like divide out that as like a quotient group under addition? I think you said you can last time. Is that right? We get a group under addition. Is that true?
so um, you, I mean, you could, I guess. I'm trying to think for a second. Um, so two games being equivalent when their difference is a number. Uh, I don't think that has been done before. Because so like that's a weird thing to do. Because if the difference between two games is a million, then like one of them is a million moves better for left than the other. Like why would you want to consider those equivalent? But you could.
Okay.
I guess you could take that quotient.
Yeah, I'm just curious about the
Well,
structure of like this hyper comparability thing. Like, so like I guess you not only have that hyper comparable set of numbers, but also like another hyper comparable set of like just all the numbers plus star. Um, like as in each number
well, no,
individually
because zero
plus.
is not comparable to star.
Right, but I'm saying like star and one plus star and two plus star and three plus star also forms another hyper comparable group if I'm
Oh,
following the reasoning
but
correctly. Is that right?
well, they're all comparable to each other, which I think is what
Right.
you asked for.
Yep.
But they're not hyper comparable in the sense that like
They're not.
star is not comparable to its options.
Oh, okay. Right.
Yeah,
They're comparable to each other,
and so
but
like that's
yeah.
yeah. Like you probably want to go to options if you're doing stuff with games. That's why I introduced that like comparable to the options idea.
Yep. That makes sense.
But good thoughts, and as I said, you know the the so-called hyper-comparable games, which happen to be the numbers, they are very important uh, theoretically. Like there are a bunch of theorems about numbers and
Hmm.
things like that that are beyond the scope of this talk. But it's an important idea. And just to be clear, you could take a number like one of those hyper-comparable things and throw in some dominated options to make it not a number anymore, but it's still equal to a number.
Hmm.
And so, like, it's not like you have, everything that's equal to a number is in this comparable world.
Right.
No, because you could throw in some, like, crazy dominated options.
Right. Cool. Thank you. That answers my question.
Sure. Yeah. And I guess the last thing I'll say that's kind of related. So you were talking about, like, modding out by the numbers, which is kind of weird because you don't want to consider a game with much bigger benefit to left as equivalent. But the opposite is actually something that you could really do. Basically, you could mod out by the infinitesimals instead. Like, if two games are so close that their difference is less than, you know, one half and a quarter and an eighth, and greater than negative a half and negative a quarter and negative an eighth, then like it's practically zero. You may as well mod out by it, and like that's a thing you can absolutely do. Um, and if you do that, then like how can you simplify games then? And like that's a whole thing.
And to make sure I'm also following what you mean there, you're saying if I mod out by infinitesimals, that doesn't just leave you with the integers, right? Or sorry, the numbers.
No, it doesn't. No, there are
You still
plenty of.
use because the infinitesimals are still comparable with 0, so you still have like all this incomparable junk left
Well,
over.
star is infinitesimal, but it's not comparable with 0.
Oh shoot! Sorry,
But
what's the definition of infinitesimal in this context?
infinitesimal would just be like, let's just say less than uh, all the fractions, like 1/2 to the n, and greater than all the negative fractions 1/2 to the n, like or negative sign.
And also not 0, but
Oh yeah, and also not. Well, I mean 0. No, when you mod out by like a set of, when you're doing modular arithmetic, you mod out by a set that contains 0. So you usually do want to include 0 in
okay,
your set.
okay, yeah,
So 0 is infinitesimal, but you want it to be.
yep.
We are talking almost entirely in the surreals right now, correct? Like all this
No,
whole discussion.
very incorrect. Like, in fact, all of the infinitesimals under discussion, except for 0, are not surreals. Star is not a surreal, star 2 is not a surreal, up is not a surreal, but those are all infinitesimal. And in fact, the infinitesimal surreals do not appear in this discussion because they're not finite games.
The surreals are
Right,
once you start to
okay.
consider
And
infinite games. Is that the definition?
Yeah. If you take away the finite criterion on the games and then take numbers as the hypercomparable games, you get the surreals.
Is there a name
got it.
as opposed to surreals for the set that we are discussing here regarding finite games?
I mean, the numbers, the finite numbers, the dyadic rationals.
No.
all...
I'm saying the rationals, including the things that are confused with 0, just like all of the potential games that you can get. Like, is there a name for that number system? Like
I mean, finite games. The class of game values is suggested in chat.
The class of game values.
Like,
I
if you
guess-
want
I guess
games
that's
up
the
to
word I'm looking
equality,
for.
like, yeah, game value. So the word value here usually means equivalence class under equals.
Okay.
So
Yeah.
like star plus star equals 0, and so star plus star has the same game value as 0, even though they're not identical, like game trees.
Mm-hmm.
So, but like the finite game values, or the finite partisan game values under normal play, or something like some phrase like that.
Right.
Individual notes, like maybe there's a PDF out there that calls the finite partisan acyclic games under normal play, that calls them the Conway games or something, like, someone might have a name like that, but that's not necessarily standard.
Okay. Yeah. There's no cute word like surreal, I guess, is the answer then.
No, because
But-
you're not typically going to be jumping contexts in that kind of major way very often. So like in an entire chapter of a book, they're just the games or the game values.
Okay.
But every game value that you could have is included in the surreals then.
No, star is not a surreal, and the value of star,
Or not.
like its quality class, is not a surreal. And like the game where left can move to -1 and right can move to left can move to 1 and right can move to -1 is not a surreal, and it's not infinitesimal. There's nothing like a surreal. Like most of the game, well, maybe not most, but because that's kind of hard to define, but like tons and tons of games under discussion are not surreals.
Okay.
The surreals are like the surreals, the finite surreals, which are the dyadic rationals, are in a way that can be made precise, kind of like the most boring of games. And there are plenty of other games that are more interesting. Like Star, even, is a hair more interesting than 0. But like the game where left can move to 1 and right can move to -1 is much more interesting. Because if left gets the first move, they get a whole extra move. And if right gets the first move, he gets a whole extra move. So like, it's really important compared to like in 3, like nothing's gonna like right doesn't have a move.
Right. Yes. 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 If you're considering actual games being played between two people, then
Yeah, that's what this talk is about, not
right.
just
Well,
the.
So sorry. The definition of surreal games is what precisely?
So a surreal is like take this definition of game on the screen,
Uh-huh.
delete the word finite, then the hyper comparable games are the surreals.
Okay, gotcha. Does that look like some kind of set of ordinals or something?
Yeah, so the surreals is like a whole separate talk if you're not familiar with it. But like it, it if you know what an ordered field is, the surreals are like all of the ordered fields glued together. Like it's a proper class size thing. It contains all the ordinals and it contains every big ordered field you could imagine.
And it's still totally ordered, right?
Yeah.
Like it's yeah.
Huh.
But like with finite, it just reduces to the rationals whose denominators are powers of 2.
Mm-hmm. And there's an implicit set here that we're also not discussing, which is like the infinite games, but not taking the what was the term you used? The hyper comparable.
Right, yeah. Like so they're like like Star Omega
Right. So that's
is
like a
like a game
non-surreal.
that's not a surreal and not finite, but you can move to any size nim heap is fine.
Okay. That's a game value which is not surreal and not finite.
Yeah. So I think you're seeing why I put finite here, because it would be like a whole other talk.
I think the reason I was getting confused is because my the little that I know about the surreals just uses the same notation. So in my mind, the relationship between the surreal numbers and then the numbers of the games that we're discussing, it was kind of the relationship between like the rationals to or the reals to the rationals, where like the I thought the surreal was the extension, the whatever of these finite games. Um, is it
Yeah.
is it
So
wrong to think about these games as numbers?
yeah, that's the thing that I kind of like was maybe saying too fast to two swap earlier. So the like the vast majority of these games are not like numbers, but some of them are like numbers. And so the
Got it.
surreals are like the ones that are like numbers when you take away the finiteness assumption.
Got it.
But
Got it.
most
Okay.
the game I said out loud, which I will type in the chat, where left can move to 1 and right can move to -1, that is like, it's very different from a surreal because for one thing, it's incomparable to 1 and 0 and
It,
-1.
it's the full
And
branch of those. It's all the options, basically.
what is what? I'm confused.
Never mind. Sorry.
But yeah, so this game I put in the chat where left can move to 1 and right can move to -1, this is a game and it's not like a number. It's not like a number for a couple of reasons. One, it's incomparable to some numbers like 1 and 0 and -1, and also all the numbers in between, like a half.
Yes.
And the other,
Okay.
and another way, it's not like a number, which is, this would maybe be like a follow up talk about how games that act like numbers work. But like in a number, you typically don't want to move because you'll just use up your move. Like if you have the number 2, if left moves in that component, they'll just use up one of their moves and it'll be down to 1. Like you don't want to move in a number if you can avoid it. But a game like this, you probably do want to move because if left gets there, left locks in another move for herself. And if right gets to move there, right locks in another move for himself. So you kind of do want to move in this game, even though you don't want to move in a number game.
Mhm.
So there's a whole world of games that are not like numbers, and star and up are just like the tip of the iceberg, but there's many more.
Got it. Okay. I'm following now.
I'm curious. Is there a way of like, is there some formal name or function defined which sort of gives a numerical value to games of the sort like the one that you've written? Uh, Wait, sorry, I'm confusing myself on the notation real fast. One on the left and -1 on the right. That's good. That is. Did you just say that's not good for whoever plays first?
No, it is good for whoever
Okay,
you
yeah.
want to be the one playing
Left
first
gets
there.
left plays first and gets 1, and right plays second and gets -1. So you want to go first.
No, yeah, like left plays first and moves it to 1, and then left has a move saved that she can use anytime, and there's no more -1 anymore.
Right. Um, is there so my question was going to be, is there some function that is defined which gives a numerical value that maybe the range of incomparability sort of makes this impossible or something, but like I'm wondering if in Go, um in the end game there's an idea that a position has a certain point value regardless of its sente or gote status, um despite like there being a set of possibilities underneath it. And I'm wondering how you formalize it. And the answer might just be there isn't a way to, or maybe you can only do it for some tiny class of things which are like incomparable or infinitesimal when subtracted from one of the numbers, one of the proper numbers. I'm wondering if there's a function that would map from this thing to 2, basically. That's what I'm asking.
So that's an excellent question, and that's like also tied into like maybe like a whole nother follow-up talk. What I will say is so one concept which I think is what you're kind of searching for is the mean value of a game. But it wouldn't send this to 2. It would send this to 0. Because if there were 2 of these, so if we consider, Go, so actually I could be very cheeky and say if there were 2 of these, it's me-I.
Right, yeah.
So, like, left could move in one and secure a move for herself, and then right could move in the other and secure a move for himself, and those would cancel out.
Right.
And so because in a sum of like multiple copies, this averages out to 0, the mean value of this is 0. But if you had like 2 and 0, then the mean value I think would be 1 probably.
Right. So like
so there's that.
That is an interesting concept. I don't know if that's exactly what I'm searching for, because like what I'm trying to think of, as Go players, we're usually in the end game. In practice, what a lot of people will do is you'll look at each position, compute its point value to whoever, like rather the difference of point value depending on who goes first, and like you'll probably object to that. And say,
okay.
In general, that's
so.
not. Yeah, sorry.
So, what you're saying, there's another concept, which, so I think, like maybe there should be another talk that gets into mean value, and then the thing you're getting at is something called temperature.
Okay.
Temperature is kind of like, how urgent is this? Which is like the difference in the values that, like, the 2 players would get based on who goes first. So those are 2 different things you could measure about a game.
Would the temperature of the top one be 2?
Yeah.
Oh, cool.
No, because that's another talk on cyclic games. So the problem here is that, like, we had like 4 other people show up this time. If this becomes like a course, there's going to be like 2 people left.
Well, I'm going to be one of them.
Okay. I'll think about it. Maybe I'll alternate or something.
Yeah. You should teach. This is good.
I mean, I do teach.
Is that your job?
No.
Oh, okay.
Yeah,
Well, okay.
that's, I think, enough for the video.
I meant you should be like a professor.
I have taught college courses before.
Okay, that explains it. It feels like you have.
Sawdust, you had something?
I thought I did, but I changed my mind. I
Okay.
do second the motion, though, that you do teach like a skilled teacher. Kudos.
The slides are pretty too.
Thank you. This is the default Beamer theme.
Well, I mean pretty in. I don't mean pretty in uniquely in the visual sense. It's well designed. I mean.
Sure. All right. Well, I think we covered some good stuff, and could perhaps cover more stuff about, say, temperature or things
Yeah.
like that in a future talk. But I think it's a good time to call it.
Yeah, I appreciate it.
Cheers. Thank you very much.
Thank you.